So, yeah, pretty simple. And then you'll see in more complicated things, they'll tend not to show you like the negative lead right here. Instead, we'll go something like, let's see, what's a simple circuit I can draw for you? We'll go with, I don't know, I'll draw this as I go along. But we're going to see those 3 lines like I did before, usually in circuits like this, in a DC circuit, because it just makes it more neat. You don't have to draw all these wires coming back. So there's a positive again, right? And so let's say, let's make a, maybe we'll make a, we'll have a switch here, which is closed at the moment. That will go through. If this is 9 volts, right, we're going to have, say we want an LED right here. There's an LED, right? But there's a component that's missing right here. So let's say if we just give 9 volts to an LED, it's not going to go over very well, because the LED, it's made to turn on at 3 volts. After you go over 3 volts, it's going to want to draw more and more and more and more current. And an LED, usually most standard LEDs are only going to be able to take 20 milliamps. So you don't want to give it any more than 20 milliamps. And then sometimes if you go over that, it might work still, but you're going to shorten the lifespan by a considerable amount. So we add in a resistor, or in this case, it would be called a current limiting resistor. So we need to do a little bit of math here to figure out what our resistor value would be, right? So we're going to use probably one of the most simple electrical equations, which is V equal to IR. This is voltage is equal to current times resistance. Current is represented by an I, so let's write this out. V is equal to voltage, or voltage is sometimes called electromotive force. I is current, and R is resistance. Probably can't read that because my handwriting's horrible, but whatever. Yeah, so we have V equals IR, right? If we're using 9 volts, we're going to do, and just like a regular algebra equation, we're going to do 9 is equal to our current. We want 20 milliamps. So this is going to be represented as, this is usually represented in amps, or amperes is the full way to say it, amperes. But I'm going to call it amps. And this is represented in amps, but we want to write this as milliamps. So we're going to write this as 0.002. I think that's right, yeah. Right? Yeah, 0.002 is 20 milliamps. And then we're going to do multiplication. I'm going to write this as a dot. Or you could do this, the x, it doesn't matter. I usually don't do an x because it's going to get mixed up as a variable, right? So, and then we have r, which is our not known value. So you're just going to solve this like a normal equation. 0 minus 0.002 minus 0.002, and you're going to get... I don't want to do the full math behind this because it's a really weird number, but one of the tricks that I use is every volt, when you're calculating for an LED, which I do quite often, every volt is 50 ohms. So if we have 9 volts, I can tell you that 12 volts is 600 ohms. So this would be... this would be about 350 or 400 ohms. So, yeah, 400, yeah, this would be 350 ohms is our ideal one. If you can't find anything, if you can't find a 350 ohm resistor, then sometimes you might be able to substitute something a little bit higher or a little bit lower. It's okay. If you do something a little bit higher, it's not going to be as bright, but sometimes that's not going to matter. You know, if this is just like a power indicator light, it's not going to matter. So we'll have R1, 350 ohms. There, that's going through our LED. This gets bled off to ground. Right. So, and then say, this is going to turn on a, let's say we want to turn on another type of load. So say that this is gonna, what can I think of here? Of a circuit that might, let's have this turn on a relay. So I'm gonna have this turn on a relay. Okay. Now there's 3 terminals on a relay. There's your common, then you have normally closed and normally open. I usually you would think, well, why would you want a normally closed? You know, because don't you want the switch to do different things? Well, some applications you might want it normally closed. Can't think of any on the top of my head right now, but there are some applications where you might want to use that. But yeah, so this is going to be normally open is represented as NO, and normally closed is represented as NC. So now, with our circuit, let's say we're switching 120 volts AC, right? And this is going to power something else. So let's go from normally open as well. So I'm going to go around my shitty equation there. Let's see. What if we do, yeah, so I'm gonna do this as AC, which is, notice how I use this symbol right here? This is what AC is. It's a sinusoidal waveform or a sine wave. And so it can often be seen represented as this, which is made to be a sine wave, or this is sometimes called like a tilde or other things. It's, yeah, whatever. Right, and so this is our L going in, our live going in, and then this is our live coming out. So I'll draw the sine wave like that, right? So now, as this is coming out, let's say we're gonna power, what can I think of? Something that this relay is gonna power. Let's say that this relay is gonna power, if it's 120 volts AC, let's say it's gonna power some kind of, I don't know. Maybe we're gonna have a light bulb turn on, and then, you know, how about a strobe light? You know, so we can have a, this, you know, Halloween's coming up, but what about a strobe light? So have this go like that, right? And then, you know, usually, like, we'll cut this right here. And then we'll have, you know, some kind of driver circuit to drive the strobe light, you know, and then, this is also going to need another AC input, another AC output, which is the neutral. So that's going to go there. And neutral is the returning for an AC, for AC. So, yeah. It's just like DC, the negative and positive must return to the negative, but you can't just connect it like that, because then you're going to short it, and that won't work. But when you go through a load, anything in a circuit, a resistor, a motor, you know, a motor is called an inductive load. A motor or transformer, you know, anything, electromagnet, the LED, anything, that's a load. And so if you can, you know, yeah, that's a load. So any load is usually not going to short your supply. You know, unless you're like AC, in some AC applications, say you know, connect the secondary of a transformer instead of the primary, AC's, it's not going to work, it's not going to like it, and it's going to think it's a short. So, most likely you just melt that out, or you're going to trip a breaker. And let's see, what else can we think of here? Oh, yes, the other equation that I will make of note. This video is getting a little bit long, so I will do this as quick as I can. The other equation that is very, very useful is P is equal to VI. And so this is an equation that you can use to figure out. Sometimes you'll hear the word watts, which is P is power, and so that is watts. And so watts is the product of voltage times current. So that means that both of those are combined, and watts is power. Now, it's not always watts. You can have VA, which is volt amps, and that's what transformers are often measured in. There's a lot of different ways that you could go about that. But let's say, you know, let's say, for you know, your circuit. Here, let me show you. Let me get my power supply out here, and we can get a visual representation of what all of these different things are. My power cable. Okay. The power supply for the power supply in. There we go. Okay, now this is starting up. There we go. Okay. Now let's find a load to power. Well, anyway, I'll find a load in a second. There's a lot of things we can see here. We have this at the top, these green ones. This is, and it has V, that's voltage. The yellow one with the A is amps, and this one down here is watts. So let's find a circuit that we can power. Here's a relay. This tiny little guy here, an Omron relay, fairly standard part, right? So this coil voltage, we're going to look at, especially at relays, you want to know what its coil voltage is, so that's it right there, 12 VDC. So that means 12 volts DC is what its coil voltage is. So this power supply is already set for that. So let's turn that off, and then we can connect this to the coil. This one's a bit weird. It's not like relays that I've used before, and how it where the coil contacts are. They're usually at the back here. They're usually these two. But let's give this thing power. Okay, you heard that click. Now this is a load. We have right there at 12 volts. We have this is 31 milliamps right there, right? So 0.031 amps, that's 31 milliamps. And then we have down here our watts. So that's the product of our voltage and current. If you did the math there, you'd figured out that, yeah, 12 volts times 3.1 amps is going to give you around 0.37 watts. So yeah, that's just, there's your application there. AC, it's a little bit more complicated in AC to get your power, to do power and other things in AC, because AC can sometimes, AC uses what's called real power and then apparent power. Usually I don't bother trying to go through all of the math for trying to calculate real versus apparent power, because real power, because it often, this equation is just going to give you your real power, which is what your device is actually consuming. So let's see. Let's say we have a, say I want to, let's calculate something like, say, you know, I want to find out how much power a device is using. So if I know my voltage, say, you know, it's 120 volts AC. So 120 volts, right, is equal to P, right? And then our current, we can find out with like a current clamp or another meter that will measure current, right? So let's say we have 120 volts at 2 amps, and then we have our P value, right? This is going to give us 240 watts. Right? Very, very simple to find that out. You know, and then you can always do because this is an equation, it works in any way. So any variable, you can swap out. So, you know, if you don't know what P is, but you know, well, no, that's what this is anyway. Let's say you don't know what your current is, but you know what your power and your voltage is. Well, then you just sub in, instead of our variable as P, we'll just put, you know, we'll put whatever our value for P is. So, you know, 240 watts is equal to 120, right? Times I, right? That'll work, right? You know, we divide, we can divide some things here. So, you know, the goal of any equation is get the variable by itself, right? So we can usually, right here, we can divide 120, right? 120 will give us 2. There's your current right there. 2 is equal to I. There you go. So yeah, very simple, simple stuff right there. Just thought, you know, some people thought that would be helpful for some people. All right, catch you on the next one. See ya.